Alright, alright. Let's use this. Let's look at some things that we can get from uniform circular motion. And so let's look at some uniform circular things that we have. A useful thing to talk about is the time it takes to complete one revolution, or this is sometimes called the period. And we'll have a useful way of measuring things. We have a period, which is time, and 1 over the frequency. And frequency is probably going to be a new thing that we're going to talk about. It happens often. It's one thing per unit time. And so we get this reciprocal relationship. There's a unit for that called hertz. Some of you used this in chapter 1 when you were looking up how to determine how often a heartbeat was, or the period. You would use hertz. Well, now we're going to formally introduce hertz as a definition, and it's how often something happens per second is what the hertz does. But we're going to have this concept of frequency, how often something happens. And in our case, we're going to talk about the frequency of how often we come around in a circle. Right? I work my way around a circle once, right? That's 1 revolution, and I can talk about the frequency of my revolutions. That also means we can look at our definition of velocity and say, hey, it's distance over time. And so instead of trying to catch little infinitesimal vectors, what we can do is we can figure out how long it takes to go around once. Right? 2 pi r is going to be 1 circumference divided by the time of 1 period. And that'll give us the velocity vector that we have. And this is useful for things that are very hard to measure the direct line on. When we do a lab with this, it'll be easier to count your rotations over a certain amount of time. And so this is the easier way to get the velocity vector out of it. We'll see this in practice, but let's use this in a system. And so what we're going to do is we're going to look at the acceleration of the moon. Right? The moon is being accelerated towards the Earth. Back when Newton talked about this, the way he said it was the moon is falling towards the Earth, but it misses. And the orbit of the moon around the Earth is nearly spherical. So put oblate spheroid Earth. Whoops, I thought I changed my color. Why is that not changing the color? Right, what is the Earth? The big blue marble? So kind of sort of in the center there, there will be the Earth. And let's be pedantic, let's give it some landmass. Right, there's some green landmass in there. So this is really an Earth. And we'll give it a moon orbiting out. And since the moon is made out of cheese, I made it green. And now what we're going to do is we're going to work on what the acceleration is towards the moon. How fast is the moon falling towards the Earth? What is the acceleration? And it's not 9.8, right? 9.8 is only good near the surface of the Earth. What we want to find is that acceleration that the moon is having. Now the moon, let's see, it does revolve right-handed, and so we need to figure out how to calculate this for the moon. And so we know that AR is going to be V squared over R. And NASA did a really neat thing at one point. They went out and they put some mirrors on the moon, and we shine a laser back to it, and we can measure how long it takes the laser to go back and forth. So there's some things we know about the motion of the moon, very detailed. But there's another thing we know, is that it rotates all the way around in 1 month. Roughly 1 month. And so what I'm going to do is, you know what? That velocity is the same as 2 pi r over the period squared, right? Because if v equals 2 pi r over the period, I'll replace v there, and then I just have to divide this whole thing by r. And we're going to get something that pops out a lot in astronomy. I'm going to get 4 pi squared. If I square this, I get 4 pi squared. And loads of astronomy problem when it pops up, and this is why. In fact, pi squared is a common thing within rotational motion. Divided by t squared, my period squared. Now I'm going to have an r on the bottom and an r squared up top, so that's just going to become plain r. And so I can simplify the motion of the moon. And so if I look into the tables, I can say, hey, the moon has a radius away from the Earth, or its distance away from the Earth, is 3.84 times 10 to the 8th meters. And 1 month is 30 days, so let's see, 30 days. Well, if we look on the table, a month will use to be 27.3 days. There are 24 hours in 1 day, 60 minutes in 1 hour, and 60 seconds in 1 minute. And so I can come down here, and for my t squared, I'm going to multiply all those together, and so a month is 2.36 times 10 to the 6 seconds. So I'll square that. And I run screaming over to my calculator, and I get 2.72 times 10 to the negative 3rd meters per second squared. Now what I can do with this acceleration due to the moon, well, I can compare this to g. And so we can say, how many g's is this? So if I take this and divide it by 9.8 meters per second squared, let me get my zeros right, yep, 2.78 times 10 to the negative 4th, or roughly 3/10,000ths of a g. So a sub r is 3/10,000ths of a g. And if I take ar over g, where I'm going to divide this. And so the moon is falling towards the Earth really slowly. Well, the acceleration is slowly. And then later we'll look at what this means for force. Right? We now have its motion. We can now talk about the force. Because, hey, didn't we learn something earlier? F equals ma? We now have the acceleration that the moon is feeling. We know its mass, so we could be able to figure out the force. And this is what Newton did. He said, hey, we'll call that gravity. But then we're going to do more with circular motion than just gravity problems or astronomy problems. I know I have an astronomy degree, so I'll bang on about it a little. But we'll do multiple things with this. But for right now, this is where we're starting.